So thank you very much. So this will be an introductory talk. I will introduce the pentagram map and discuss the related topics. And then the rest of the day we will also discuss some things related to the pentagram map. So the first part, number 0 of my talk, is called, in Latin, pentagramma mirificum. And this is the name that Carl Friedrich Gauss used in 1876 to describe the following picture. So following other people, for instance, Napier, Gauss considered two-dimensional sphere and a rectangle triangle on it, spherical triangle, rectangle. And so, inspired by some Pythagoras ideas, he studied the geometry related to it. And the picture Gauss decided to draw was the following. So he took these two vertices of the triangle and then draw a circle polar to each of these vertex. Next, he extended the edges okay. So, and the figure we get here is a pentagram. So that was one of the first appearance of a pentagram picture in math. Then, so Gauss calculates the length of this interior pentagon. So this will be called alpha, beta, then gamma, delta, epsilon. So actually it's squares of tangents of the length, but doesn't matter. And he discovers that these 5 numbers satisfy some relations. For instance, alpha times beta equals delta plus 1, and then 5 more relations cyclically, calculated cyclically here. Also, so Gauss tells us that so we have only 2 degrees of freedom remaining instead of 5 numbers. Okay, it's easy to calculate. So he tells us that this set of relations is actually equivalent to the fact that the following map, let me take, so we have 2 degrees of freedom, so I take 2 numbers as coordinates, alpha and delta, and then I will send it to delta plus 1 over alpha, so it's one possible way to write this map, alpha plus delta plus 1, alpha delta. And so the statement is that this map, sometimes called Gauss map, is 5 periodic. So let us keep it on this blackboard, and we will see how these calculations of Gauss are related to the rest of my talk. So now let me start the regular talk. So the story, the modern story, started in 1992, where our chairperson, Rich Schwartz, started to consider, so he actually invented what he called a pentagram map. So the pentagram map is the following map. So let us consider a convex n-gon in the plane. Then we take the shortest diagonals and we cross them. What do we get is another smaller n-gon here. So this is the map, actually. This is the map. So let us denote P, this polygon, n-gon, and so this interior polygon will be denoted T of P. So T is a map. Well, so if we iterate the procedure, then it will rapidly shrink to a point, actually, because the n-gon becomes smaller and smaller. But we can observe that, of course, this construction commutes with the action of the group of projective transformations, which is SL3. So I don't want to specify the fields SL3R or complex situation SL3P, SL3C if you prefer. Okay, so actually this tells us that, first of all, we should not take the Euclidean plane in this construction. We should consider the projective plane so that this action is well defined. And second, instead of acting on n-gons, we will act on equivalence classes of n-gons. So our space, the main space, is denoted Cn. So this is a space of n-gons in the projective plane where I take the quotient by SL3 action. So this is also, we can say, moduli space of projectively equivalent n-gons, if we prefer. So, and the map T is well defined, because since it commutes with the action of SL3, so it is well defined on this space. Well, very well. So the main results about this map I'm going to discuss today is the following. So theorem. The map T is a completely integrable map. So completely integrable means in the usual Liouville, or should I say Liouville-Arnold sense, it means that there is a Poisson bracket and commuting first integrals. So we will discuss this. It's the most classical way to define the integrability. So it was proved first in 2008. So that was a conjecture, actually, of Rich. Because so Rich studied, I will tell this maybe more in detail. So Rich studied this map for many years, actually. And he discovered a lot of nice properties of it. So, for instance, he discovered first integrals. He discovered a natural set of functions, polynomial functions in some natural variables preserved by this map. And he also discussed the map is recurrent and many other properties. And so he conjectured that it must be integrable. Actually, the conjecture was also based on computer experience. So actually, it's even better than a proof, as we know, because a proof can contain a mistake, but computer doesn't make mistakes. Okay, so nevertheless, so digressing, we will prove it. So in 2008, first result of integrability, but it was not the solution of the initial problem. Actually, we simplified. So the result was, so it was our paper with Sergei Tabachnikov, who is also here. Tabachnikov, so Richard Schwartz, and myself. But we simplified the situation. So first of all, instead of this complicated space, modular space of n-gons that I'm going to discuss, it will be the main subject of our discussion today, we considered a bigger, larger space, which I will denote Pn. And so this Pn is also the space of n-gons, but it is a space of twisted n-gons in the projective plane, also quotient by the same action of SL3. So twisted means that the n-gon does not close, actually. So more precisely, a twisted n-gon is a sequence, infinite sequence of points, and P2, with the property that Vi plus n not exactly equals to Vi, but up to some map, which is an element of SL3, and it does not depend on the choice of this point I. So if M is identity, then we get a closed n-gon, so what we considered initially. But here we fix some monodromy, and we get a twisted n-gon. And so the space of all twisted n-gons means the space of n-gons with this property, but we don't fix M. So M can be arbitrary. It is fixed, but it is arbitrary. Okay. So this space is actually much simpler, and we can even prove that actually Pn is nothing but the Euclidean two-dimensional space, provided n is not a multiple of 3, which is also an important restriction. But at least in this particular case, it's a very easy space, simple to study. So first we prove the integrability on this Pn. So actually, to the people who are familiar with infinite dimensional integrable hierarchies, KdV, or some more complicated equations, so they know that monodromy is very important. So it's not just by chance that monodromy appears here. It is an important ingredient, but it simplifies a lot. But then we had to wait 3 years, and so we proved it the same result on Cn, and independently the same result was, or similar result was obtained by Fedor Solovyov, who is unfortunately not here because of some visa problem. So Solovyov also proved integrability, but by completely different methods. He actually found an L-Lux representation for this pentagram map acting on n-gons, and he subtracted information from this Lux representation. Okay, now so let me give a couple of examples. So examples of the pentagram map. The first case when the map is non-trivial is if we take a pentagon. So this is the origin of the name pentagram map. So now we can draw the diagonals and obtain here a pentagon. Then we can iterate the process. So this is the map. Okay. Now, so this is the first time where this projective equivalence is very important, because let us look at this picture. So we consider this vertex, for instance, and we compare the smaller pentagon with this corresponding vertex. So let us look at the picture. So actually, what I'm trying to explain here in this first example was already known to Greeks. And Greeks' theorem, all of them can be proved by just a nice picture. So this is what I'm trying to say. So if you take our pentagon exterior and here obtain this smaller pentagon, then it is projectively equivalent. So the result of the pentagram map is a projectively equivalent pentagon. Because so it is completely, the situation is rigid. It is completely defined by the pentagon defined by its diagonals here. And as you remember, there is only one projective invariant of a pencil of 4 straight lines, namely the cross ratio. And the cross ratio is the same here and here, because it's just equals to the cross ratio of these 4 points. So it's the end of the proof. Therefore, what does this mean in our situation? So if we take a pentagram on this space C5, which is 2-dimensional, so to itself, then actually this map is identity. It's an identity, the identity map, just because the result is the same pentagon modular projective equivalence. So of course this is the best, perhaps the best example of an integrable system. So next, so second, hexagon. So if T maps acts on a hexagon, so Richard proved that actually it's not identity, but it is an involution. So the square of T is identity here, also integrable. The first non-trivial case, so the first non-trivial example is actually the case of heptagons. So it's not at all trivial here, and Richard observed quasi-periodic motion here. So in this situation, computer experience gave some complicated motion, but so the picture was very similar to this. And so of course this is evidence for integrability. Okay, but so it is not periodic here. Eh? Yeah, so dimension of, yeah, let us, by the way, let us discuss this. So as I told you, it's a complicated algebraic variety, Cn, that I'm going to discuss in details. But let us at least calculate the dimension. The dimension of Cn. So we have n points on the plane, 2 times n, but we have to subtract the dimension of 3. So it is 2n minus 3. And here, yeah, I'm, for some reason, thank you, 2n minus 8. So 14 minus 8 is what? 6. So it is 6-dimensional discrete dynamical system here. Okay. Well, so now, okay. So all this is very nice, but the question is: so why on Earth should we study this particular dynamical system? Why? Well, so the first reason is that the figure is magic, and so people associated 5 elements to it. There is, as you know, Earth, water, air, fire, and the last one, spirit. Well, for Russians it means something else. But there is another reason for it. There is another reason. So as you remember, if you turn wrongly this magic picture, it becomes an evil sign. so-called goat or dragon pentagram. And then, so now it becomes more scientific. So actually, so what I'm drawing, so this is a pentagram map, which relates many different subjects of mathematics, of geometry and algebra. So it is, of course, related to projective geometry. So it also both elementary projective geometry and projective differential geometry. It's also related, of course, it's, as every integrable system, to symplectic or Poisson geometry. It is very closely related, as we will see, to infinite-dimensional classical integrable systems, so infinite-dimensional as KDV or Boussinesque. And therefore, it is related to such algebraic structures as double algebras, Virasoro algebra, Gelfand-Dicke bracket, and many other things. Moreover, it is also related to the very fashionable modern part of algebra called cluster algebra. And it is also, on the spiritual side of the story, it is related to Carl Friedrich Gauss and Coxeter. So now I'm asking everybody try to find the one-to-one correspondence between the picture. So, well, some vertices are very easy, for instance. Here, okay, but some other are also quite clear. Okay, now, so before I'm going further, let me mention, so there will be 4 more talks on related to the pentagram map. So I will just very briefly mention so contribution and of different people. So there are a huge number of papers related to this pentagram map now, and so besides Rich, there is an important result of Max Glick, who I hope will explain us his results. So Glick studied the pentagram map on this more simple twisted space of twisted polygons, and he established the first clear relation to the cluster algebra that we already conjectured, by the way, in our first paper on the subject. Then also, so Solovyov I already mentioned. Together with Hessin, Boris Hessin, Solovyov and Hessin, so they considered higher pentagram maps, they call it. So geometric construction in higher dimension than dimension just 2. And they are integrable. So Gloria Marie Bifa, who is here, also contributed to this, to the study of these higher pentagram maps. So among other things. So I hope she will explain us something about this story. Okay. So there is also a still unpublished paper of Fock, Vladimir Fock and Marshakov, who consider the framework of Poisson-Lie groups. And so this will give some multi-component generalization of the pentagram map related to R matrices, so Poisson-Lie groups. So also Rinat Kedem will explain us, hopefully, the relation to another relation to cluster algebra, dynamical system arrays in cluster algebra, so-called T systems. Well, so as I say, of course, higher pentagram is very important, but there is also low, I would say, lower pentagram. So little brother, I say ugly brother, ugly little brother of the pentagram map, but who also desiring to become very famous. So it is due to 4 people: Gechtman, that I already mentioned. So Gechtman, Shapiro, and Weinstein, so three musketeers working on cluster algebra since many years, and also Sergei Tabachnikov. So they defined and studied a map where the projective plane is replaced by a projective line, actually, and it is also a very interesting integrable map that will be important. Okay, so there are many other works that I hopefully will mention later. Good. So now, okay, the second part of my talk is called the space Cn. So, as I mentioned, so it's a complicated space. So let me write here again what we are talking about. So we are talking of configuration of n points in the projective plane. Actually, of course, in many considerations, we can replace projective plane by a projective space, okay? And so we take the quotient SL3 or SLK plus 1, more generally, okay? So the only restriction, so it's not just arbitrary n tuple of points, but we don't want to three consecutive points belong to the same line. So they should not be on the same line. Otherwise, we don't know what is a diagonal, okay? So this is the only restriction. So this manifold actually has a famous story. So actually, this kind of manifolds, maybe to some subject to some conditions of non-degenericity, were studied by many people. For instance, by Gelfand and Macpherson, who showed that it is related to the Grassmannian. So here we have Grassmannian of three-dimensional spaces in n space, quotient by the maximal torus, which is n minus 1 here. So I'm not going to describe this in the details. So this is just to give you an idea. Now, so we will take another road to study this space. Actually, we will use the projective geometry to understand it. Okay, so from the point of view of projective geometry, so first I take Pn, the bigger but more simple space of n-gons. And so the statement is here that the space of twisted n-gons on the plane is just nothing else but the space of linear difference equations of the following form. So this is the first statement. So I put minus for some aesthetical reasons. So plus 1 minus plus vi. So what is written here? So v is an indeterminate. So vi is a sequence of numbers that we want to find, and a's and b's are known coefficients. So I want, so by definition, both sequences A and B are n-periodic. So, okay, and so this is a space. This is a vector space, or affine space, as we prefer. So the space of these difference equations, very well known in mathematics, so very, very classical. And actually, the claim is that these two spaces are isomorphic under the same restriction n is not multiple of 3m. Okay. So how to do this? Very shortly, very briefly, I try to explain you by drawing a picture. As in Greek time, we will prove theorems by drawing a picture. So we have an endpoint here, or some maybe twisted n-gon, I plus 1, so on. And so what we do, we want to lift from the projective plane to the three-dimensional space, which is now a capital Vi plus 1, and so on. And so we can do it in many different ways. But so we will impose one condition, normalizing condition. So this, if we take three consecutive vectors in three-dimensional space, three consecutive points here, so we want, by definition, that the determinant of this three vector, so it's equals to a constant. For instance, 1 equals 1. So this is our condition, and so this is a starting. So this was a statement. Now here, this is a proof, an idea of the idea of the proof. So if we can do this, then every coordinate of these points will give us a solution. And so this lifted n-gon in the Euclidean three-dimensional space will be the fundamental system of solutions to this equation. And actually, so we prove this is possible if and only if n is not a multiple of 3 for some reasons. Okay, good. So, so this is our simple space. What about Cn? So Cn corresponds to the those equations that have periodic solutions. Just because we are dealing with a closed n-gon, not with a twisted n-gon, some monodromy, but closed n-gon. So this is the same space of third order difference equations, but with periodic solutions. So yes, so, I'm sorry. In general, of course, the solution is not periodic. Even if we ask that the coefficients are periodic, the solution has not to be periodic, of course. But it has to satisfy some periodicity conditions. So actually, we have a monodromy. So necessarily, every solution will be a linear combination of the initial solutions. Shifted by n will be a linear combination. So m is an element of SL3, the same element as the monodromy of a twisted n-gon. So here, just with the monodromy equals identity, or in other words, periodic solution. So this is our space. This is now our space we are going to work with. Okay, and so we already have two interpretations. One is geometric interpretation, which is here, and another one is analytic. How to say, please? So m is fixed for every two n tuples of coefficients. You necessarily obtain one element of SL3, which is a fixed matrix. Yeah. Right. Of course. I agree. Right, correct. So we can express it as as it will be a 3x3 matrix with entries which are polynomials, quite complicated polynomials in A's and B's. Yeah, actually it is very important, and Richard Schwartz used this expression, precise, explicit expression, to obtain the first integrals, the quantities which preserved by the pentagram map. So, okay. So far there's no condition. So you take any equation. Yeah, AB arbitrary, and you will get automatically that can be calculated explicitly by quite huge expressions here. Yeah, so Thank you. So we already have two different ways to describe this, but we will need another one. So this is analytic way. So this is a geometric way. So algebraic way is also needed. Okay. So now, very briefly. So this. What about the lower dimensional situation? So if we replace P2 by P1, so then the space is a very famous space, sometimes called M0n. So the same definition, but with projective line instead of the projective plane. So n-gons in the projective line. So this is an important space, and the corresponding difference equations are also well known. So instead of third order, we have order 2 here, and there is only one coefficient, AI. So it is called Sturm-Liouville or Hill, discrete Sturm-Liouville or discrete Hill equation, or discrete Schrödinger, whatever you prefer. So, and the statement is the same. So if you wish to deal with closed n-gons, then we want the monodromy to be. Thank you. I also want some comments from non-experts. So, of course, if we want the n-gon to be closed, so we need to ask something. And amazingly, it's not exactly the same condition. It's almost the same. So it has to be closed on the projective line, but not necessarily lifted polygon in the Euclidean space should be closed. So here the condition is M is minus identity for some reason. So it's also an element of SL2. So the group, of course, is SL2 instead of SL3. Okay. So this is how to say, the younger brother of our favorite space, Cn. So, but it is very, very famous. So many people studied it, of course. And so, of course, compactification is the most interesting problem here. Okay. So there are different ways to compactify it due to some many famous algebraic geometers. Okay, now so already we know this space. So when we started to look at the pentagram map, the first question actually was just to understand where do we live. So we looked at the continuous limit of it. So let us suppose that n tends to infinity. So n goes to infinity. Continuous limit. So n goes to infinity. Then we replace an n-gon by a smooth curve. Okay, so our initial data is a smooth curve, say gamma, in the projective plane, and the condition that 3 points does not belong to the same line is that there is no inflection points on this, so it's locally convex. Now. So we take a point here, say gamma of x, call it. So we will choose a parameter x, gamma of x. Then I take two neighboring points, gamma x plus epsilon, gamma x minus epsilon. Okay. Then I draw a chord, and I take a convex envelope of all my chords, so I get another curve. Okay, that I denote a gamma epsilon. So this gamma epsilon is a new curve, gamma epsilon, L also parameterized, so it will parameterize our curves. Okay, of course. So now we have a family of curves, and we can say we have a flow. We obtain a continuous dynamical system, a flow on the space of curves. Okay, but now how to write this analytically? So we should, oops. So we should do the same. Not easy to manipulate. Okay, we should do the same as we did in the case of angles. First of all, so what does projective geometry tell us? A curve in P2 gamma modulo, of course, modulo projective transformations. It is the same, and this is very classical. It goes back to 19th century. So that to every such curve, we can associate a third order differential operator or differential equations, which I right here. So it's linear differential equation. Y is an indeterminate function in X. Okay, U and V are periodic potentials, periodic coefficients, smooth functions here. And so old people in old time told these are projective invariants of the curve. So they called U the projective curvature, and so V is related to some projective lengths. They also told us that it's better to consider, instead of considering V of X, we consider just some skew symmetrize this operator and take V minus U prime over 2. Yeah. Now, so if we take this as a infinite dimensional coordinate system, then what we get an evolution on this two functions, this space labeled by these two functions. And then we can differentiate with respect to epsilon, so the kind of usual procedure. And so we did this. And so what we get is the following formula. So so maybe it was not a good idea to call it epsilon, but maybe some t, some other new second parameter t, time. So we differentiate with respect to t, and so what we get, we just calculated and obtained the following system of nonlinear differential equations. So that was the first, just the first idea to understand what's going on. And so then we looked for several seconds at this equation, and we recognized it. We just identified it. It is a very classical and old Boussinesque equation, which is the oldest integrable systems. It is several years older than the Korteweg-de Vries, for instance, equation. And it was only 4 years after Carl Friedrich Gauss. So Boussinesque, this is a Boussinesque equation. Now we know what are we talking about. And actually, it's a huge part of mathematical physics to study discrete Boussinesque equations. So there are several dozens, maybe 100 of people studying different versions of discrete Boussinesque equation. And so they are not aware and will never be aware of existence of pentagram map, because you can discretize one given continuous system. You can discretize in infinite different ways, and then you can argue which way is the more beautiful. So we know, but they don't. Okay. So actually we used this immediately. And so this allowed us to use, so since Boussinesq equation is known for 160 years already, it allowed us to get many information about it. For instance, we obtained the Poisson bracket. The Poisson bracket. So for Boussinesq, there is not only one, but it is so-called bi-Hamiltonian system. So there are at least two, actually a hierarchy of Poisson brackets. And there were works for Semyonov-Tinishansky, Frenkel, Rishtikin, who discretized the so-called second Gelfand-Dickey bracket. So we decided, why don't we discretize the first one, which is simpler? And so this is what we did. And we obtained a Poisson bracket written in coordinates A and B explicitly. And the bracket is so for some reasons it skips 3. Sorry. So it's a sum, of course, over repeated indices, AI, AJ. So this is the bracket between two coordinates, A and B. Then A's and B's all commute, and B's is the same formula for A's, but with the minus sign. Okay? So this was the Poisson bracket. And then we took the invariance calculated by Rich, and we proved the Poisson commute. So that was the end of the story for the integrability on the simple space of twisted n-gons, where A's and B's are is a good coordinate system. But the story for this, our main space was much longer. So I just mentioned the subject related to it. So, and this is why mathematics is actually beautiful, because people do many different things and they don't know that they are related altogether, but indeed they are. So in 1970, Coxeter defined the notion of a frieze pattern. And this is the following. So it's a table of numbers, an array of numbers. So first he puts a row, infinite row of ones. Then he puts here some numbers, arbitrary numbers, A1, A2, A3, so on. And then it continues infinitely to both senses. And then he calculates the next row, which is here in the middle. So the next row with the following diamond rule. So whenever you see A, B, C, D, you want the determinant to be equal to 1. So CB minus AD equals 1. So this allows us to calculate the next row, it's polynomials in one, the next, and so on. And so we can continue to infinity. But if here we have a blackboard which prevents us from, what if, is it possible that for after some computations, so we put here A's, some sequence of A's, and after some computations we obtain again a line of 1, and then the frieze pattern is closed after some number of steps. And this is a theorem which implicitly proved by Coxeter and Conway in 1972. Coxeter and Conway proved that the frieze pattern closes up if and only if AI's are coefficients of a Sturm-Liouville equation, which is no more on the blackboard. With anti-periodic solution. So it was not explicitly in this paper, but we interpreted with Sergei and with Sophie in this way. And so we have another third way to describe our space Cn. This is the space, just the space of closed Coxeter frieze pattern. And this was crucial to understand the relation of the space to the cluster algebra, because the space of Coxeter friezes is actually a cluster manifold. And so we also have here some symplectic or presymplectic structure, which is just the structure considered by in the cluster algebra. Okay, so this is actually this. So this what the combinatorial way to describe the space of Sturm-Liouville equation, or in other words, this baby, this little brother M0n to our space. So we did the same procedure, approximately the same procedure, but with more complicated friezes corresponding to Cn. We also have a cluster algebra structure. We also have some symplectic form omega on it. And so there was an immediate hope and conjecture that this symplectic form is exactly what we need. So because the Poisson structure we obtained from this Boussinesque discretization of Boussinesque, it is well defined on Pn, a bigger space. But if we want to restrict it to the space of closed n-gon, it doesn't work well. So we want a symplectic, genuine symplectic structure defined on this on our space Cn. And so we have one given by the cluster algebra structure. It was exactly our code. But so to our big surprise, we calculated explicitly the action of the pentagram map on the our cluster manifold of friezes, and it turns out that it does not preserve the symplectic structure there. So only this younger and small brother, calculated by 4 musketeers, and which operates on this younger brother of our moduli space, or on this classical Coxeter frieze, it does preserve the corresponding symplectic form. So it is one of the examples then where, so as I told you, to study the pentagram, we need all of these ingredients. And here it actually, there is double iteration between the map and the corresponding cluster algebra. Actually, not only the cluster algebra gives us information about the map, but also the map gives us information about the cluster algebra. It tells us that the canonical symplectic form defined in the cluster algebra is actually not the only possibility. There should be something else, but nobody knows what. So this is one of the main exciting problems that we study. Okay, so now there are many other problems. So my pentagram would not be complete if I don't mention the relation to Carl Friedrich Gauss. And this will be the very last point of my talk today. So if you remember that, you remember the first encounter of Faust with Mephistopheles. Faust drew a pentagram to discuss some matters with Mephistopheles, and it was incomplete. And this prevented Mephistopheles to leave the room. So we are not allowed to leave the room until my pentagram is incomplete. And it will be if we understand what is the relation to the Gauss pentagram. Okay, now let us look at this series of relations, and let us organize this alpha, beta, gamma, delta in some array again. So I put alpha, beta, gamma, delta, epsilon. So these are our numbers. Then I continue delta, epsilon, alpha, beta, and so on periodically. And then I put ones here. And what do we get? So if we ask the same frieze, Coxeter frieze relation, here what do we get? We get exactly the relations obtained by Gauss. So that was the main motivation for Coxeter actually to define his frieze patterns. Okay. And so it's a very amazing relation here. Also, what about this Gauss map? Actually, the Gauss map is the following. So we can take coordinates here, and coordinates, so enough information to calculate the whole frieze pattern. How can we do this? For instance, we can fix alpha and delta, then beta will be calculated from the first round, then we can calculate epsilon, and so on and so on. And so this Gauss map is nothing by the shift. The shift, and this is why it is 5 periodic, just because the frieze pattern is 5 periodic. Okay, so this is the first example of so-called equivalent to a T system. So Gauss never considered this as a dynamical system because there is no dynamics here. It is just a periodic map. And this is the case for all periodicity conjectures in the cluster algebra, the homological periodicity, and so on. It's always periodic, and it always can be obtained in a similar way. Okay, so now I think the pentagram is closed, and you are allowed to leave if you wish. Thank you.
Thank you. I have many mathematical questions which I want to ask you later because I don't want to spend the time between the talks. Only one non-mathematical question. How it is possible? The first, I was shocked by the date, 76, because Gauss died in 55. Of course, I know pentagram and devil can...
Yes. Please. So maybe it's the year of publication of collected works, actually. Yeah.
I don't know whether it's canonical answer, but this paper of Gauss was not published when he was alive, so it was included in his collected work. And yeah, I have a copy of this, if you are interested. That's the date.
You are right. Yeah, so this is the date of publication. So sometimes it happens that publication is posthumous.